In the last couple of videos, we saw that how force postulate is used to calculate various parameters, correct? Like radius, velocity, energy, and all those things. But remember, whatever we calculated, it is for the stationary orbit, right? Radius of nth orbit, velocity of nth orbit, and the energy of the nth orbit. But what we understand is that whenever we give energy to an electron, then what's going to happen? It's going to jump and then it's going to return back to its original position. In the sense, suppose say an electron is in the first orbit, then it's going to absorb energy. It's going to go jump to the second orbit. For a brief duration of time, it's going to be there on the second orbit. Then it returns to the first orbit. Now, what we have is there is an energy change. There is an energy difference. Correct? This energy difference, it comes out as some sort of a radiation. Okay. Now, every radiation has a particular wavelength and it has a particular frequency. Correct. So, what we have is that E, the energy, h nu is equal to E2 minus 1. Okay, the change in the energy is basically the radiation emitted. H nu can be written as hc by lambda is equal to E2 minus E1. Alright. Now, 1 by lambda, that is 1 divided by the wavelength, 1 by lambda is equal to, see the value, this into 1 by n2 square minus 1 by n1 square. 1 by lambda is equal to this into 1 by n1 square minus 1 by n2 square. Now, how we got that value is because remember you did energy. In the last video, we had derived the energy. We apply that energy formula and this is what we get. Okay, now what is N1 and N2? N1 is going to be the first order. First in the sense, from the initial orbit. N2 is going to be the final orbit. Okay, there is jumping the initial orbit to the final orbit. Correct. Then it returns back to the original orbit. In the sense, in the initial orbit. Now, 1 by lambda is equal to that. You're seeing that huge value, correct? That huge value is basically constant because look at it. Every value in that given thing, it's a constant value. So that constant is what we call as Rydberg's constant. Okay, I'm sure most of you are familiar with Rydberg's constant from last year's chemistry. Correct? Same Rydberg's constant is this. And the value of Rydberg's constant 1.097 into 10 to the power of 7 per meter. Alright. Now that 1 by lambda is what we call as wave number. So mu dash is equal to r into 1 by n1 square minus 1 by n2 square. Now guys, this is a very important part because we are going to discuss about the energy level diagram. Okay, based on how that jumping of the electrons is going to occur. It's a very simple concept. Alright. See here, suppose if n1 is equal to 1, okay, and n2 is equal to 2, 3, 4, so on and so forth. In the sense, electron is in the first orbit, then suppose say an electron from the second orbit jumps to the first, alright, or from third to the first, whatever it is. If the electron is jumping to the first orbit, then n1 is equal to 1, n2 is equal to 2, 3, 4, so correct. So we get 1 by lambda or mu bar is equal to r into 1 minus 1 by n2 square. This type of radiation comes in the UV region, ultraviolet region. Okay, and the series is called Lyman series. Okay, now bottom line, what you have to understand, for Lyman series, n1 is equal to 1 and it comes in the UV region. Okay, suppose if n1 is equal to 2 and n2 is equal to 3, 4, 5, so on and so forth, this comes in the visible region. Okay, the energy, suppose if an electron jumps from third to second, fourth to second, like this, it is jumping and jumping. The radiation comes out in visible region and this is called as Balmer series. Suppose if n1 is equal to 3 N2 is equal to 4, 5, 6, so on and so forth. This comes in the near infrared region. Okay. This series is called as Paschen series. Okay. Next one is, suppose if N1 is equal to 4, N2 is equal to 5, 6, 7, so on and so forth. Okay. This comes in the infrared region. And this series is called as bracket series. Suppose if N1 is equal to 5, N2 is equal to 6, 7, 8, so on and so forth. This comes in the far infrared region. If N1 is equal to 5, N2 is equal to 6, 7, 8, so on and so forth, then this comes in the far infrared region. Okay, this is called as fund series. P silent here. Okay, it's called as fund series. Now we understood that for different types of jumping of the electrons from one orbit to another, we have different types of radiations, correct? Now we can understand this with the help of the energy. Remember the formula E is equal to minus 13.6 by n square electron. That means here for the first orbit, suppose if n is equal to 1, then we have minus 13.6 electron. If suppose n value becomes 2, that means for the second orbit, we have the energy E2 is equal to, see, minus 13.6 divided by 4, correct? Which gives you minus 3.4 electron. Suppose if I have to calculate for the third one, n is equal to 3, then minus 13.6 divided by 9 is minus 1.51 electron. See, so on and so forth, it decreases, correct? Keeps on decreasing. Suppose if n value becomes infinity, then the energy is 0. Correct? Look at this energy level diagram. Okay, now you can clearly understand how the jumping of the electrons will occur. In the sense, second to first, third to first, it keeps on jumping. It comes out as UV. This is the Lyman series. Correct? The first part, what you're seeing. Suppose if N1 is equal to 2, see the arrow marks, everything is pointing to the second part, that is N is equal to 2. That is the Balmer series. Isn't it? Now, as you look into this energy level diagram, let's look at what is written on the left side and the right side. You see the orbit and you're going to see the energy of that particular orbit, isn't it? So, this is what we call as energy level diagram. Now, again, I'll tell you what you should notice in this energy level diagram. First, notice the orbit, which is n is equal to 1, 2, 3, which orbit you are in. Second thing you have to notice is what is the energy of the orbit. Okay. Third thing what you have to notice is that from where to where the electron is jumping. Okay. And the fourth thing you have to notice in the energy level diagram is that what series is that particular jump. In the sense, Lyman series, Balmer series, what series are we looking? Okay, so these are the four key points in energy level diagram. Understood? So this is about what Bohr's theory is about, because we started with the postulates. Using the postulates, we calculated what is the radius, velocity, blah blah blah, everything. Then, with the help of that energy, we calculated when one jumps and returns back, what is going to happen. Okay. Now, this is the most successful atomic theory because based on Bohr's postulates and Bohr's atomic theory, lot of other theories were developed. Okay. And also, de Broglie also proved the Bohr's second postulate. And how he proved, we are going to look at the next week.